Hello, ladies and gentlemen. We're now on, um, we should be on chapter 4 having to do with moments. And maybe I forgot to change the title slide. And indeed, we are on moments. So, title slide's got to change. Moments, also known as torque. In physics, they call it torque. Whatever force you have perpendicular to some lever arm, force perpendicular to lever arm, the lever arm length times that force will give you a torque. That's your magnitude. If the force is parallel to the z-axis, but still perpendicular to the lever arm, will you have an applied moment? And the answer is yes, but your wrench won't move because it's being opposed by an opposite torque. It's like pulling up on the door handles of a door. You're applying a torque, but there's a reaction torque. There's a reaction moment. If you grab the top of the door and the bottom of the door and you try to twist it, you'll have the same thing. You will be applying a positive torque because you'll have a lever arm, you'll have an axis of rotation, but the hinges will oppose it. So you won't be able to move the door. Only if you have a force that is perpendicular to the axis hinges will the door move. Okay. So, and that'll be important sometimes. Just understand that. We can apply the force up and down here, right here. You will apply a torque, but you will apply a moment, but it won't move because the wrench is constrained. There's an opposing moment. And you could try to twist this wrench also. You could try to twist it, but it won't move because there would be an opposing moment. Now, there is another situation. If you try to push parallel to this axis, you're not generating any moment because you would have a zero distance. You would have no lever arm. The force would be parallel to this line. No lever arm. That would be zero moment. Okay, let's keep going. If you're at an angle theta to the lever axis, you have this distance here is d sine theta. Here's the line of action of the force. And you just take distance times lever arm. Still gives you the magnitude. And this goes into what I was talking about earlier. If the force is parallel to the lever arm, you'll have zero moment because theta is 0 degrees and sine of 0 is 0. Here is the right-hand rule. So now we've talked about magnitudes so far. So let's get into the vectors. And here's a picture that you have your lever arm this way. You curl, you have the lever arm going out like so, the force going like this. Your fingers wrap from the lever arm to the force. Your thumb points in the direction of moment. That's what this is. You have A cross B, that your fingers curl from A to B, and your thumb points in the direction of C to get A cross B. Okay. Moment is perpendicular to both the lever arm and the force, the vector moment. Okay. Here's other ways to look at the right-hand rule. A cross B. Point your thumb in the A direction, your fingers in the B direction, your palm points in the C direction. A cross B equals C. In this picture, point your thumb in the A direction, your fingers in the B direction, your palm points in the direction of the vector C. Your palm points in the direction of A cross B. Move your middle finger, pinky, and ring finger perpendicular to your thumb and forefinger. And if your thumb points in the direction of A, your index finger points in the direction of B, the other three fingers will point in the direction of A cross B. And finally, if you just use three fingers, your thumb, index, and middle. Now I find that a little clumsy. I would rather use this picture because I'm manipulating my hand and I've got bending the ring and pinky into my palm isn't as comfortable. Just letting the three fingers point in the direction of C is fine with me. Thumb in the A direction, index finger in the B direction, and middle finger in the C direction. Either way, take your pick, or use the curl from previous. Take your pick. All of them do the right hand rule. So a couple things to note about the moment. You have coplanar forces in the XY plane, then the moment is in the Z direction. You can just add up the moments. If you have a counterclockwise force like F1 and F3, counterclockwise, that's positive. It's in the positive Z direction. If it's clockwise, it's negative. And a lot of times people won't use the vector description of moments. If they're in a single plane, like an XY plane, they'll just use clockwise and counterclockwise. Counterclockwise is positive, clockwise is negative. Okay. So here's an illustration. Well, determine the moment for each case. So this figure right here, 2 meters, 100 newtons, and we'll consider the z-axis coming toward us at point O, so that would be 200 newton meters. And since it's clockwise, it should be negative. Now, why are they showing positive? That sounds like a book answer that's wrong. It's tending to rotate the thing clockwise. Okay. I don't think the book is, I think they're just using the absolute values right now. They're not into the positive and negative signs. I will go into positive and negative signs just to illustrate what's going on here. They use this symbol for clockwise. Here's a symbol for counterclockwise. Positive, negative, negative, negative. So they denote it differently, which is okay. Number B, the force is along this line of action, the dotted line, 0.75 meters. So it would be 37.5 Newton meters, and it would be clockwise. Let's see what it says. 37.5. This doesn't make any difference. The 50 newtons is parallel to this. No lever arm. Okay, 40 newtons times 4 plus 2 cosine 30. Get your calculators out, figure it out. That's pretty easy. So it'd be that length, that lever arm, times this force will give you approximately 200, I'm guessing. There it is, 229. I was a little off. Okay, that was just doing calculations in my head, not a calculator. This one here, it is in the XY plane, so this is a thing that's bent. That's 0.707 times 60, which is 0.4242. It's in counterclockwise, so it would be positive. 0.4242, positive. I just happen to know this 1 over the square root of 2 is, and which is a sine of 45, is 0.707. After 50 years, 60 years of doing this stuff, you kind of get some numbers stuck in your head. Now, 7 kilonewtons, 3 meters, 4 meters up, 1 meter down. This doesn't matter because the lever arm is parallel to the force. So it's only the 3 times 7, 21 counterclockwise. 21 kilonewtons this time. Kilonewtons. Notice the kilonewtons on the force. Okay. So now we want to add this up. I personally for these kinds of problems, I like to use Excel. So let's do that. I will set up an Excel spreadsheet with all the forces and everything. I changed my mind. I'm not going to do it right now. We'll go to the next video. We'll pick this up on the next video.